is that morphology can increase evolvability. So I mentioned we're evolving a lot of these behaviors. Evolvability is a term that means your given evolutionary system is more evolvable than another evolutionary system. It can more often find a good solution. It can continue to adapt to changing conditions in the environment in which these creatures are evolving and so forth. This is a somewhat surprising result because in the image on the left here, we evolved bipedal locomotion where the morphology or the mass distribution of the biped was fixed, and as you can see, it doesn't do a good job. We then placed the radii of each of these cylinders under evolutionary control, so the dimensionality of the search space has increased, and the number of possible solutions now has gone up. So the search space is much larger, but given that larger search space, we were actually able to find better solutions more often. This is a better solution, but not a perfect solution, as you'll see in a moment. You can see with the widths here, it tends to move the mass distribution down, but there is also considerable mass up in the torso, right? So it's trying to cancel torque while it's moving, something that we do while we walk. So again, by including this additional evolvable parameters, typically you would think that would slow search because the dimensionality of the search space is larger, but because it has control over morphology and the neural controller, it's able to find better solutions more often and more quickly. Okay, here's another fourth line of reasoning about why morphology is important. As David mentioned, changing body plans in physical robots is difficult, but it's not impossible. This is the self-reproducing machines project in which I was partially involved with at Cornell. You can see here that the robot is able to change its own topology. There's a lot of interesting modular robotics projects that are going on now in Europe and the United States. By changing its own topology, this robot is able to physically construct a copy of itself. Okay? It's a very simplified version of self-reproduction in that we're assuming that the raw material in which it's made up of is readily available to it, which of course is not true in reality, but it's a place to start. Okay? So if we assume a robotic platform where the topology of the body plan can change during behavior, there's lots of new behaviors that become possible, like physical self-replication. Okay, I've already mentioned the Resilient Machines project. Here, the evolution, as I mentioned, is going on in simulation. And like the previous example that I showed you, our robot here starts, this is more like a developmental system than it is an evolutionary system. We have a physical machine that begins by moving randomly, sometimes known as motor babbling in child development. Based on the sensor-motor correlations that it discovers through this motor babbling, it starts to evolve the topology of its body plan. We're assuming it doesn't know how it's put together to start with, discovers that it's a quadruped, then uses that discovered self-model, where it uses a second evolutionary algorithm to internally rehearse or use mental imagery or mental simulation to come up with the locomotion pattern, and then tries it out in reality. So there's, again, some similar methods here. We're assuming here there's an explicit self-image or body schema, if you like. But the nice thing here is we can introduce truly unexpected change. We can damage, we can pull off one of these robots' legs. It's something it truly wasn't built to experience. And even though it might not be able to directly sense that damage, so we're assuming our robot doesn't have a camera, it can't see or feel the fact that it's been damaged. There are changes, obviously, in the sensor-motor correlations. It uses that to re-evolve a simulation where it simulates itself as a 3.5-legged robot rather than a 4-legged robot. Re-rehearses a new behavior given its damaged state and is able to autonomously recover from damage. So we can pull off a leg and this robot learns to walk again in a different way. So again, morphology affords new kinds of competencies that are difficult if the robot is not changing its assumptions about its body plan. Okay, sixth line of evidence. This is from some work in my lab, my PhD student Joshua Auerbach, where again, if we adopt certain body plans, like the ones that you see down here, where now we have a segmented body plan. So there are 3 segments here. They're actuated segments in the spine. Each segment has attached to it 2 actuated legs. If we assume a segmented body plan, the question is, we want our hexapod now to locomote towards this object and manipulate it. And how is it going to do that? In our case, we went from quadrupeds to bipeds, and our front appendages have specialized away from locomotion. We tend not to use our arms for locomotion very often. However, that's one solution we find.